Alright, morning. Let's get it started. Alright, so let's finish the unit step function, and then I'll introduce another type of function called impulse function. And just a quick review on unit step function. This is the definition. So we use u of t as a symbol to represent this unit step function. So please don't use anything else, okay? So in this class, when you see unit step function, we're talking about u of t. Okay? So u of t could, in general, could be anything else, but for this class, it will be unit step function. Its definition is it is 0 when t is less than 0, and is 1 when t is greater than or equal to 0. That's unit step. Graphical wise, basically you have a 0, 0, 0 until t equal to 1, t equal to 0, and then there's a jump, right? The step change until it reaches 1, and then continue to the right as a constant 1. Okay. That's what u of t is. So what do we use u of t for? Okay. There are many different applications. Okay. One of the applications in control system, later you will learn, is basically we use it as an input to the system. It's actually a very special input. Later you will learn, unit step input contains many different frequency spectrum. So that can be used as a good indication of system input. Okay, and then you look at the output of the system, you actually will get a lot of good information out of the output corresponding to this unit step input. And the other type of application is, at least for now, is we can use u of t, okay, and even combination of several of them, addition, subtraction, and then we can use them to represent piecewise functions, right? For example, we learned, if you have f of t, which is a exponential function, then alternatively, we can represent this f of t as e to the power negative 2t times u of t. So that will basically give you this f of t instead of writing this piecewise. And as a matter of fact, right? As a matter of fact, for any f of t, okay, for any f of t, when you use this f of t time u of t, so let's say it gives us a third function. Let's call it w of t. Okay. So if you have any function f of t, and then you use it to time multiply u of t, okay, of course it will give you another time function. Okay. But the nature after you do the multiplication, this w of t, as we learned actually in the signal property, this w of t in nature will become what kind of signal? It's a causal signal, okay? Because nothing left, right? Nothing on the right left side when t is less than 0, right? Only everything on when t is greater than 0. Okay? So that's the usage of u of t. When you use u of t time anything, you produce a causal signal. And we also had an example here, basically, and I show you how to create a cookie cutter, right? So if I have u of t, so suppose we have u of t at here, and you can have a negative u of t minus 1 at here. Then together, when you add these two curves together, or right, when you use the u of t minus u of t minus 1, so this curve plus this curve, we create ourselves, okay, this is 1 at here. This green one here is u of t minus u of t minus 1. We created a box, okay, a rectangular box. Okay, this rectangular box is very special. It can be used as a cookie cutter. So cookie cutter basically means when you multiply anything with this box, everything outside the box will be gone, will become 0. And anything within the box will not be changed, will still the same as your original curve. Right? So that's what we call this is a cookie cutter here. Right? So f of t, let's see, for any function, then f of t times u of t, and then u of t minus 1, right? Like this. Okay. Graphical wise, okay. So this is what it looks like. If this is your box at here, then really we don't care what looks like, okay, anywhere, you know, outside this range. So within the range, right, when you multiply this with cookie cutter, this is what's left. Right. So this portion here, let's use green one, this portion is f of t times u of t minus u of t minus 1. Okay. And this is your original f of t. So you can imagine I create a cookie cutter here, right? I mean, you can creating this box at a different location with a different bottom length. Okay, they all basically a type of cookie cutter. Okay? You just cut out a different size of cookies. Right? Okay. As a matter of fact, in the class there was in the lecture notes there is an example. We have an example right here. If we create a function f of t using 1, 2, 3, 4 unit step functions, they are basically original and then shifted by 1, by 2, by 3. Right? This function, what would it look like? You can visualize it by looking at it as if it has two parts. Okay, the first part is u of t minus u of t minus 1, and that's basically what we just drawn here, right? Yeah, and this one here is u of t minus 2 minus u of t minus 3. Okay, so basically it will have one box at here, and this is u of t minus 2, u of t minus 3. You could actually draw this by looking. So you look at this one here. This box has a left edge at t equal to 0. Right? That's t equal to 0 here, and end up at t equal to 1. So this box should have a left edge at t equal to 2, right? And end up with the edge at t equal to 3. So this will be your f of t. So we're creating essentially two boxes. Okay. If you want to create more, you can actually use, okay, you can use this formula to create a lot of boxes. -1 to the power of k times u of t minus k, and then k start with 0. You can give it any numbers, for example 12 or 11. Actually it has to be an odd number, finished with odd number here. So 11 or 13 or 15. Okay. So you can basically keep adding boxes, okay, behind it. Now this is, as a matter of fact, this is producing. This is what we call unit, like pulses. Okay. So if you put so many together, you're getting a pulses type of graph. Okay. Yeah. And each graph has a unit. Each part has a unit length, unit height. Okay. And another example we showed in the class is this. So let's say, suppose we have, this is what we call f1 of t. Okay. Sorry. This is a graph f1 of t. Okay. So we present a piecewise graph f1 of t, and you can describe this f1 of t using piecewise language, saying f1 of t equal to 0 when t is less than 0, and f1 of t equal to this part, and this part is basically t, right? When t is between 0 and 2, and f1 t will be 0 again when t is greater than 2. Okay, that's how you would describe this piecewise function. Now, since we learned the unit step function now, and we learned the cookie cutter, so I can represent this f1 of t, okay, using one single expression. Essentially, to cut out this straight line here using a cookie cutter at here, right? So cut it out, and that's what you have for f1 of t. To cut it out, basically you use this curve, this function t times the cookie cutter. In this case, it's u of t minus u of t minus 2, right? With the length of 2 at here. So this portion is what I call the cookie cutter here. Okay. So that's much simpler, right? In terms of mathematically. To further this little bit here, let's say we have another curve, okay, which is this. Okay, so let's say we have, this is what we call, this is f2 of t. So if you have f2 of t, another piecewise function, it's 0 when t is less than 2, and between 2 and 3 you have this straight line at here. So this straight line itself, you can easily derive that is negative 2 bracket t minus 3. So that's the straight line equation here, because it passed this point 2, 2, and also past this point 3, 0. So that's the straight line equation here. And then go back to 0 after t greater than 3. And that's piecewise again. But if I use this cookie cutter concept, so we're going to cut out, right, only a portion of this straight line. That portion is between 2 and 3. So we're going to cut out just a portion of this by multiplying this straight line with a cookie cutter. So in this case, what will be this cookie cutter here? U of what? Minus u of what? T minus 2? Exactly. Okay, very good. So this is f1, this is f2. Okay, and and very often you actually have a curve called f of t. So going up first, then going down next. So when you put this f1, f2 together, you get this triangle here. And this triangle, you can describe this triangle using piecewise language. F of t equal to 0 when t is less than 0. F of t will be t when t is between 0 and 2. And f of t will be negative 2t minus 3 between 2 and 3. And 0 again when t is greater than 3. However, as we have just learned, you can just simply add these two things together, right? To represent this triangular curve. So that gives you t times u of t minus u of t minus 2, and then minus 2 times t3, u of t minus 2, and u of t minus 3. Okay? So this is the idea for now, right? What the unit step function can be used as at least to simplify the expression mathematically. Let's take a look at a different example. Any questions? Yes? This graph? Oh, this graph? Yeah. This graph, basically, you have a curve f2 of t, 0, 0, 0, and then go up to 2, right? And then drop it down to 3, drop it down to 0 again at t equal to 3. So this portion is a straight line, which is basically part of this straight line here. Okay? Yeah. If I want to just express f2 of t, basically I just need a cookie cutter right here. And in this case, I'll use a black one. So I just need a cookie cutter between 2 and 3. So when you multiply this cookie cutter with the negative 2t minus 3, guess what? Nothing else exists except the part between 2 and 3, which is this portion here. That's what happened, right? So this times this will give you this. That makes sense? So if you still feel a little confused, I would suggest that you graph these two separately. Okay? So you have these two graphs. If my question here is, can you multiply this graph and this graph together? What do? You use, if you pick any point, you're going to use that point and multiply the corresponding points here, right? But this is all 0 here, all 0 here. And this is 1 here. So only which part exists? 2 to 3. Between 2 to 3, you're really multiplying 1 with whatever here, which is this. And that's what you want, right? Yeah. Okay. All right, so let's take a look at a different example here. Okay? And this example, let's calculate what is the convolution between any function f of t and the unit step function u of t. And we're going to assume f of t is causal. Let's calculate this in convolution here. So slowly actually we'll come back to convolution. F of t convoluting u of t. So first step, treat u of t as if a generic time function like g of t. Okay. So you use your formula for convolution. Okay, just write down the formula for convolution. Formula convolution here is 0 to t f of tau, and then what's next? U of t minus tau. And by the way, this is one thing I have mentioned also to students coming to office. Can you write down the formula for convolution? Right. So if you hesitate, I mean you can't. You can't hesitate. So if it's 1 minute, you can write maybe more than 10 times, even 20 times. So that's the fundamental. You have to be able at least to write down the formulas, right? Yeah, you're not going to get this formula. So this is your convolution formula based on purely just the definition. Okay. Then, as you recall that when we do convolution, we basically used the graphical approach, right? A graphical approach, essentially we graph this. We also try to graph this one. Now graphing this one, the step is basically to graph u of tau, and then graph u of negative tau, and then to graph u of negative tau minus t. Right. Now that's the graphical approach steps, from here to here, and then from here to here. Yeah. If I try the graphical approach as I show here, as what we did. So first, what's u of tau? U of tau is this. Right, this u of tau. And what will be negative u of negative tau? Right. Okay. Then what will be the last one? U of negative tau minus t. So shifting this u of negative tau to the right by amount of t. Okay? Yeah. So this is a u of negative tau minus t. Is that good? Yeah. Okay. So now we multiply this graph. Right, this is 1 here, always 1, huh? With f of tau, okay, with f of tau here. So when we do the last step, doing the multiplication between these two graphs, or the two functions, and the next logic step is we look forward, we look for the patterns, right, of the overlap. Okay. So in this case, it really doesn't matter what this one is. So you look at this graph. When you multiply this graph with another function. In this case, this function is assumed to be causal, right? Causal means this function has nothing on the left side, only something on the right side. Okay? So, for this function f of tau, it's basically something on the right side there, right? So when you multiply this and this, the overlap, doesn't matter what the t is, right? The overlap is always between 0 and the t. So that's 0 to t, we don't have to change. And what you multiply f of tau with what? With the value of 1, right? So this function is always 1 between 0 and the t. So you can replace this function with 1, right? That's what unit step function is. So f of tau times 1. And times 1, you don't really have to write it, but so it basically becomes 0 to t f of tau d tau. So your convolution of any function, any causal function with the unit step function end up with just the integral of this function from 0 to t. That's actually a pretty neat finding. So you can also say it differently. The convolution of any function with a unit step function basically give you the area of this function, right? From 0 to t. Okay. You could remember this one more or less just like a formula, right? Yeah. So convolution between any causal function and unit step function give you back the area of this function f underneath the function f from 0 to t. Okay. So that's another example. Any questions so far? Okay. All good? Yeah. All right. So now we look at a different function. Okay. Yeah, called impulse function. Okay, none of the function, first of all, none of the function like a unit step function or impulse function, especially impulse function, as you will see. Okay. Physically, you actually cannot even create in the real world. Okay. But mathematically, it's a very important function. You can use it for so many different applications. Okay. First, let's write down the definition. For impulse function, we will use delta. Okay, represent. So you write the delta like this, starting from the bottom, and then it goes up. Okay, that's your delta. So delta t will be used exclusively for impulse function. Okay, so in this class, whenever you see delta t, it doesn't mean anything but impulse function. And the definition essentially says delta t will be 0 for t is not 0. And for t is 0, it's infinite. And sometimes in textbook they call it undefined. Okay. And I will actually illustrate the next one here. If you integrate from negative infinite to positive infinite, integrate this delta t. Okay, so if you integrate this impulse function, you will get 1. You will get 1. I think I need to emphasize is definition. And well, I'll explain how this is definition here, but I do recognize a lot of time, especially when you learn new things, our brain tends to not accept these new things. But we are rule followers. So when you see definition, you should tell your brain, follow it, because that's definition. There's nothing else I can do unless you define something new and accept by everybody else. So this is a definition, then you got to accept it now. Okay, so parking ticket, I got to pay for it, right? So that's the idea. That's a rule. Now, where is this impulse function come from, right? So I'll give you a little bit a demonstration here. Actually, parking ticket, you don't have to pay all. You can dispute. Okay, so let's say I have a box at here. This box has 2 edges. It's symmetric, about the t equal to 0 axis. The 2 edges at negative epsilon over 2 and then positive epsilon over 2. So we call it. It's a small error. So sometimes we use epsilon, this Greek letter, to represent a very small quantity. The height of this box is 1 over epsilon. So now we create a box at here. So then next we're going to do is this. we will let epsilon go to 0, shrink it, make it smaller and smaller. Right? So if we do this, you can visualize what's going to happen. Let's see if epsilon becomes tiny bit of smaller, then the bottom length of the box will actually will become smaller, right? But then the height is 1 over epsilon, so the height will become a lot higher. Okay? And as it goes smaller, infinitely approaching to 0, so this box, okay, so this box, you won't be able to tell anything at all at the bottom because the bottom length will become basically 0, right? And then the height will become what? Infinite. So we will draw an arrow, okay, pointing up, okay, representing this scenario as epsilon go to 0. And this arrow right here is basically the definition of the impulse function. So essentially now when we see impulse function, you can write down this, or you could just like what I did here, you draw a red arrow, you know, at this t equal to 0, okay, pointing up, indicating infinite upwards. Okay. Good. However, okay, but you still want to convince yourself, even though this is just an arrow, right? You still convince yourself the bottom length, it's not really arrow, it's still box. The bottom length of the box is what? Is this minus this. And the height of the box is this. And now, if I ask you, what is the area underneath this box? Or this box, which it doesn't look like a box anymore, right? What is the area underneath the box? What do? Essentially, you're calculating the integrals of this impulse function. Okay? So if you look at the area underneath these boxes here, they're all the same box except the different epsilon. So this minus this is epsilon, and then times the height 1 over epsilon. The box of the area is 1, right? It's 1 here. And that essentially, it's not a proof, but that kind of tell you where this integral equal to 1 come from. Okay? So this is a definition of impulse function. It's impulse, right? And it has infinite length at a t equal to 0, right? And the integral of that delta t from negative infinite to positive will be 1. Now this is negative infinite, this is a positive infinite, okay? But really you don't really have to integrate from negative infinite to positive infinite. You could maybe pick a point here, maybe pick a point here, right? As long as these 2 points contain that box there. Okay? But for impulse function, this is at t equal to 0. The bottom length of the box is infinitesimally small, right? So this integral could also be written as 0 minus 0 plus. Okay. It could also be written like this. And if you don't feel safe, you could also write a to b, and then you say a to b, right, contain t equal to 0. Okay. So all of this should give you the same results of integration. Good. So let's call this as a comments here, and this is one of the comments. Another comments, okay, based on what we just did here. we started the box symmetric to t equal to 0. Right? And it doesn't matter how small this epsilon is, your box will still be symmetric to this t equal to 0. So delta t, right, even though it's just arrow, it's no different from this box here. So it means delta t should also be symmetric to t equal to 0. So when you have a function that is symmetric to t equal to 0, we call that, this is a what kind of function? It's an even function. Okay? It's an even function. The nature of even function is when you replace the t with negative t, you actually didn't change the function. It's still the same function. So a very common one, for example, y equal to t squared. Right? It's a parabola, okay, going up, and that's an even function. And when you replace the t with negative t, and you get back this t squared. Okay? So this is the nature of a delta function, impulse function. It's an even function. Okay. So those are about the definition. So let's take a look at some applications of this impulse function. Okay, some examples what we can use impulse function for. For now, the first one is we can multiply a function, okay, with delta t. Okay, we can multiply a function. Let's not call it delta t. Let's call it with an impulse. We can always multiply a function with an impulse. Okay, let's observe what happens if we multiply a general function, any function, with an impulse here. Okay? Yeah. So let's say this is my function f of t. And f of t is, okay, let's see now, continuous at t equal to 0. So it has something at t equal to 0. Basically, that's what it means. Now, if I use f of t multiplied by delta t, so let's examine what happens at here. First step, you go back to the definition of delta t. So delta t basically says when t equal to non-zero value, there's no value defined, right? It's all 0. And that's the definition here. Okay. And when t is 0, then there is something, but it's a very big value, infinite. Then if you use any function to multiply with the delta function, so when t is not 0, the result of this multiplication should be 0, right? Should be 0. So basically it will be 0 when t is not 0. And when t is 0, okay, you're restricting basically only to one moment now, t equal to 0. So it's like f of 0, right? Yeah. And then times delta t. So that's basically what happens here. So in writing, you don't really have to write all of this because the nature of delta t has defined 0 and infinite, right, for different t value. So when you write it like this one here, you could just write it f0 times delta t. Okay. So this is what happens when you multiply any function with an impulse function, delta t. Okay, just a little bit simplification essentially, right? Yeah. And often in time, you're not just multiplying a delta t, an impulse. This is an impulse at which location? t equal to 0, right? You could multiply delta t maybe at a different location, or multiply an impulse at a different location. This is a delta t minus capital T. Yes?
What would that look like graphically?
Very, very important. So maybe, yes, that's a really good point. So what does this look like, right? What does this look like? What does it look like? We actually have to probably go back to the definition of delta t first. And this is delta t. And integral delta t equal to 1 basically means the area underneath this or this will be 1. What we call is a unit area, right? Unit area, okay? So okay, so area under the delta t is 1. So now coming back to this, f of 0 times delta t. So what do you think the area under f of 0 times delta t is? Exactly, it's f of 0, right? So you multiply a number. This essentially is a number. You multiply a number with delta t. It's like here. You are multiplying this area, or this area with a constant number. So all it does is you're scaling up this area by the number, right? So this f of 0 times delta t, you can consider this essentially, it's still an impulse, right? So this one here, it is another impulse. However, this time the area underneath that impulse becomes f of 0, not 1 anymore, right? But the area under f of 0 delta t is 1. So that's the difference. So how do I differentiate the sketch then? Okay. So let's say this is t. Okay. When you draw this, let's call this is delta t. Okay. This is delta t here. So that's how you draw the impulse. And how do I draw the How would I draw f0 delta t then? Now, unfortunately, you still have to draw this impulse at here, you know, right? But you can label this one as f of 0 delta t. So when you label this and this, you can clearly tell yourself, okay, so that basically means this is the area underneath one is 1, and an area underneath this one will be what's going on here? No. F of 0, right? Yeah. Is that clear? Yeah? So that's how you can draw this, differentiate the difference. Good? Yeah. Good question. So let's continue to my other part of the here. So what if I have f of t actually time a shifted impulse? Okay, shifting impulse. So delta t minus delta t minus capital T means you're shifting this impulse to t equal to capital T. Okay. So this is delta t minus capital T. Then when you multiply any function with that impulse at a different location, similar to multiply delta t, means you don't have anything other than any values other than at t equal to capital T. So this one should be f of capital T delta t minus capital T. So this is the difference here. Okay. Yeah. So let's say I give you a simple example here. If we have e to the power 2t times delta t minus 2. And I want you to simplify it. So what would you do? You will replace the t with what value? 2, right? Because this is t minus 2. And then you don't change this impulse here. You keep the impulse as it is. E to the power 4 times this impulse. So for any other functions, you follow the same rule. Okay. Okay. Good. Okay, I might not be able to finish the next property, but we can get started. Okay. And the next property is called sampling property. Sampling property. By the way, maybe I should come back to this, mention this again here. Now, when we define delta t, we know what it is. And when we have f of 0 or any other values times delta t, I also explain the difference now between these two here. Okay. Sometimes, okay, so this one here, we can call it the unit impulse function. Okay. We can call it unit impulse function. Why the unit is the reason because the area underneath this impulse is 1. Okay. So that's why we call it unit impulse. And when you multiply this unit impulse function with any other non-unit value, okay, all it does is essentially explode the area underneath that impulse. Okay. Sampling property is stated like this. This time we are going to integrate the multiplication of any function times delta t. So integrate f of t times delta t. We will apply that property we have just did. When you multiply any function with delta t, you get, right? You can just simplify the f of t with f of 0, and then dt. Okay. And this integral is about dummy variable t, and this f of 0 now become constant, so you can take the f of 0 out of this integral. And you're left with integration of this impulse function from negative infinite to positive infinite, which according to definition, this integral equal to 1. So you end up with just f of 0, right? And that's essentially what I have actually explained. The area under f of t times delta t is f of 0. But it does actually provide a sampling nature. So if you look at this one here, when you use f of t times this, do the integral, you're left with what? We're left with the value of the function f at the t equal to 0. So this is what we call sampling. You take out the sample out of this f of t at t equal to 0. So you can imagine if I multiply f of t with a shifted impulse function and then do the integral, I should get what? F of a capital T. So you're sampling out the value at the t equal to capital T. So this is why it is called a sampling property. Okay? Yeah. So we'll continue from here next lecture. Any questions? Okay.